All right, so
Here we go.
we've been learning about isostasy and eustacy. So let's be clear on the difference between those two terms. Mike, or no, Russ, what's isostasy?
Excuse me. I used to know this.
It is the moving up and down of the...
Sure, it's the vertical movement of the Earth's crust based
Yeah.
upon loading and unloading.
That's what I was going to say.
That's what you were going to say, right?
Yeah.
Okay. Okay, well, I guess I'll give you a second chance here. Define, or just tell us, what is eustacy? E-U-S-T-A-T-I-C-Y. Eustacy.
That one I don't know. I know you've told us.
E-U-S-T-A-C-Y.
C-Y, yeah. I don't know what that one is.
That's what happens when you are blind. Like when you go blind.
Oh, yeah. You used to see.
You used to see.
Oh, nice.
No.
Okay.
Guys.
Off the rails early.
Sorry.
Okay. Eustacy is simply the rising and falling of sea level because of glacial expansion and contraction.
Oh, okay.
That's right.
If we're talking about the eustatic rise or eustatic fall of sea level, the assumption is pretty much always that that's going to be a function of the growth and the shrinkage of glaciers on land. So when the glaciers expand, sea level falls, and that would be a eustatic fall or eustatic depression of sea level. Now, when you're looking at sea level, if you're standing on the coastline and you're watching the sea move in and out, because obviously as the sea level is coming up, the shoreline of the sea is moving inland, right? And so when glaciers are growing, sea level is dropping, the shorelines are moving seaward rather than landward. Makes sense, right? So
right.
The term we're going to use in this is the geological term. So a regression of the sea when its level is falling, and a transgression when the sea level is rising and the shoreline, the sea is now encroaching upon the land. So we've got transgression and regression. And so those are sort of interrelated terms. Eustatic rise, eustatic fall of sea level are going to cause transgression and regression. And that eustatic rise and fall of sea level is going to be a function of the growth and shrinkage of ice caps up on the continent. Got it? Now, for all time, for the rest of this incarnation, you will have that information.
I think so.
At your disposal. I think so.
Yeah, I think so.
I think at this point, you've got it. Okay, so all of that is relevant to what we're talking about here. Whether or not a case can be made for an actual Atlantis, a proto-historical Atlantis that would have more or less conformed to what Plato actually describes in his two dialogues, Timaeus and Critias, right? That's kind of what to set out what we're attempting here. So in order to accomplish that, what we're going to do is we're going to continue to look at the narratives of the dialogues themselves to see specifically what Plato is saying. We may sometimes refer back to the original Greek that he used, the Greek terminology, just for clarification. And then we will go into looking at what actually science can be invoked or rejected that might support or refute anything specific that Plato says. What we found so far, though, is that when you have a eustatic rise or fall of sea level, you get an isostatic response in the Earth's crust. So when you depress the Earth with the ice grows, it depresses the crust of the Earth. And when you release the ice, the Earth rebounds. Likewise, the evidence now is showing, and we begin to present some of that evidence, is that when the ice sheets are melting and the ocean level is rising, you're now increasing the loading on the ocean floor by trillions, hundreds of billions of trillions of tons of weight, literally, onto the ocean floor. You're going to get a response from the ocean floor. That's the general idea here. Now, another important idea, the geoid. The geoid is the geometry of a stable Earth, which which is always fluctuating because there are constantly forces impinging upon the Earth, both internal and external, that are wanting to change the minute, the very precise shape of the geoid. But the geoid is constantly trying to maintain moving towards equilibrium. When you have the rapid onset of an ice age or the rapid termination of an ice age, and you have this rapid melting of ice and this rapid transfer of weight from the continental surface back into the ocean basins, it causes a response in the shape of the geoid. Now, because of that, when you have the vertical movements left above or below, what's going to happen is you're going to now have a region of the crust that's now out of balance with the Earth's center of mass, if you want. The tendency then is going to be for that crustal region to try to accommodate the fact that perhaps now, if it's been unloaded, let's say you're talking about a region of the Earth's crust that's being unloaded, and let's say it's at 70 to 80 degrees north latitude, and it rises by 1,500 or 2,000 feet. Well, you can see right there that that's not the distance from Earth's surface to the center of mass of the geoid anymore. You'd have to get closer to the equator for that piece of the crust to now resume equilibrium with the geoid center of mass. So what I'm getting at here is that it's likely that from the geophysical studies of the Earth would imply that there has to be accelerated lateral movement of the Earth's crust in addition to vertical movement. You see, this is kind of what I'm getting at here. So the glacial loading and unloading is going to have pretty substantial consequences to the shape of the geoid and the response of that geoid. And this response, when you have the isostatic response, it's highly probable that you're going to have a seismic response or a volcanic or both accompanying those shifts in the geoid and those redistribution of the tectonic plates. Go ahead, Mike.
Which brings us to the question I asked at the end of the last episode about, you know, with this massive unloading of the glacial ice, the ice cap, and the loading of the water into the ocean basins, and if you posit that there was such a thing as a continent, whether you wanted to call it Atlantis or whatever, but there was some sort of landmass there, and you've got this ridge and you've got this flexion going on, right?
Yeah.
And you've got some subsidence. Surely there would be other evidence around the globe of such a major shift in the.
I'm glad you asked that question, Mike. I really and truthfully am, because that's kind of where we're going with this, and we will try to get some of that in this episode, and probably carry it over into some of the next episode to see exactly, because yes, the point is that there should be evidence. For one thing, one of the things that I would surmise is that let's say you have, as the eustatic rise of sea level presses down on the ocean floor, you're going to have an isostatic response. And that isostatic response may not be necessarily uniform. It may involve seismic movements. It may involve tremendous dislocations of along the fault line there, because we've even seen in modern earthquakes that are up, around hitting 8.0 on the Richter scale, like the Alaskan earthquake of '64. There were gigantic offsets of 30 and 40 and 50 feet, right? Now, we could be talking about here seismic events that are an order of magnitude beyond anything we've looked at in history. I mean, that, and in fact, there is some data and evidence to suggest that there were enormous seismic responses, both in, for example, the Pacific Northwest, but also in the Fennoscandian region of Northwest Europe to the rapid glacial unloading. And we can actually devote some time to looking specifically at that evidence. I don't have it right at my fingertips tonight, and that would be somewhat of a diversion. But yeah, we're definitely going to look at some stuff that would suggest that that the subsidence of the ocean floor was not necessarily a gradualistic or a uniform process, but involved discrete jumps, if you will. So anyways, this particular article came out, this paper was published in 1972, just for some perspective on this thing. And it's referring back to an article that was published by a prominent geologist named Daly back in 1925, who first was speculating about some of these ideas that are relevant to the things we've been talking about here. So I'm gonna quote here from that article here, and you'll be able to see what we are talking about here. So in a paper, largely ignored, of course, ignored in recent times, Daly in 1925 pointed out that changes in surface load over the oceans because of eustatic changes in sea level would deform the Earth. And according to Rudsky's 1889 calculations of the surface deformation of a homogeneous elastic sphere, right? Homogeneous simply means it's going to be, this is a theoretical sphere, the size of the Earth, that's going to be homogeneous, right? Meaning it's the same density and consistency throughout. Elastic meaning that it can move and respond, that it's not so rigid that it resists changing shape because of the surface loading and unloading, right? So it sounds complicated, but it's not. Calculations of the surface deformation of a homogeneous elastic sphere. So his calculation showed that the deformation would be of significant magnitude. Got it?
Got it.
So then he goes on to say that in late glacial time, the major changes in load originated from the melting of ice over Fennoscandia and North America, and the simultaneous worldwide rise in sea level from the released water. Because the surface loads involve the lateral transfer of mass, so must material be able to move laterally at depth within the asthenosphere. Now, you see what we're talking about there?
I recognize that he's saying what you were saying earlier, basically, that it can't move out and remain balanced in terms of the center of mass. Isn't that what you were talking about? It has to have some lateral motion.
Yes, but now what he's talking about is the material down even below the crust, where it becomes moltenly elastic, right? So what he's saying is that material, because the surface loads involve a lateral transfer of mass, so must the material down below be able to move laterally at depth. Okay, so in other words,
oh, I see.
Yeah, you got it. I think you got it. Yeah, you got it.
The material, the liquid material below has to be able to move around.
Right.
So think about this: is the ice is building up on North America and it's bearing down, it's pushing the plastic material outwards.
Right.
So when you're releasing weight from the ocean, you're not only the point here is that you're not only releasing the weight from above, you're now increasing the pressure from below. Because that plastic material is being squeezed to the side.
Right.
Just like squeezing a water balloon.
Yeah, it would be like squeezing a water
balloon. It bulges out, squeeze this way and bulges this way.
Yep.
Perhaps, Mike, if you could take a break and you could get a balloon and you could demonstrate that.
Demonstrate for us.
Beach ball's good. That might be easier to access.
So the point is that when, let's say, when the ice is forming and it's pushing down on the crust, you can imagine the molten magma underneath actually squishing out to the sides. And then when it melts and it's lifting back up, you're going to have this flow running in underneath.
Exactly. That's exactly it. I hope these little asides are less distracting and more useful, people. So continue on here. So Walcott goes on to say the already complex picture of relative movements of sea level is further complicated by ground movements due to post-glacial rebound itself. The material that flows into the deglaciated area to produce uplift must come from somewhere. So we would expect a complementary depression outside the zone of uplift. So now, given the context of everything we've been discussing in the last couple of meetings here, that I think is beginning to make complete sense to me.
Yep.
And why that would be relative to the question of whether or not there could have been an Atlantis, whether or not you could have had a landmass that would have risen or fallen along with eustatic changes in sea level. So he goes on to say, and then we're just about done with R.I. Walcott here. He says, if the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. Okay, let's do that again. If the whole mantle participated in the relaxation, think of that as you're removing these loads, right? And now the geoid is adjusting. So really, it's just like if you're sitting on a cushy chair right now, you know, the cushion is going to be under stress because of the weight of your ass, right?
That's
when
right.
you get off, right? If you were to stand up, are you sitting on a soft cushion right now?
Oh, yeah.
Okay, stand up once. As you're standing up, now there's isostatic compensation.
Yeah.
Think of your ass as an ice cap, right? And think of the top of the chair as North America. And this will all begin to make sense.
Bam!
There you go.
Ice Age.
There it was. That was the rapid onset of an ice age. Just like that, boom. Okay. So let's get it. If the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. But if, as we suppose here, the flow is restricted to a narrow asthenospheric shell, then the downwarp will occur in a restricted zone immediately peripheral to the uplift with large and significant displacements.
All right, you're going to have to define asthenosphere.
Well, Kyle's working on that.
Yeah.
He's
I
going to
just
give
wrote
it.
it down.
Okay, and it's spelled, sometimes it's spelled A-E, but it's usually spelled A-S-T-H-E-N-O, asthenosphere. It's the region between the crust and the mantle. And it's generally a plastic zone, which
is also the low velocity zone. Is that what they call it? The LVZ or something like that?
Well, Kyle is about to tell us.
Okay.
The asthenosphere is the highly viscous, mechanically viscous.
Viscous, yeah. You
Yes.
know what viscosity is. Okay.
Yes.
Yeah.
Highly viscous, mechanically weak, and ductilely deforming region of the upper mantle of the Earth.
Yeah. So it's what, does it give a depth there or a thickness?
It lies below the lithosphere,
Which is the sphere of rock, the crust. It's going to probably vary, 50 to 80 miles, depending. Oceanic crust is thin, continental crust is thick.
Yeah, approximately 80 and 200 kilometers, 50 and 120 miles.
Yeah, right. There we go. Okay.
Below
so that's
the surface.
The asthenosphere. It's this viscous layer that separates the mantle from the lithosphere or the crust. And it would be in this area where these transfers, let's get where you can see that, the transfer is taking place. So if the crust is moving laterally, it's moving, so crust, lithosphere, mantle down here. And here's the crust moving over the asthenosphere. Slowly in terms of continental drift, but theoretically or hypothetically, periods of accelerated motion, they're going to be accompanying the lateral transfer of mass on the Earth's surface. That's what we were referring to earlier. So his point here is that the relaxation and the stress inducement around the Earth will not be uniformly distributed, but will be concentrated in certain areas. And one of those areas would be generally very close to the region of uplift or depression. So it now makes perfect sense that as you're loading the continents with glacial ice, you're going to get an upward deformation on the bottom of the oceans, which is going to also have an accompanying complexifying effect on the level of the ocean as its bottom is rising and falling, right? Then when you have the relaxation because of the glacial unloading, you've now got loading of the ocean basins. And that, in other words, if you may be, the water may be rising over and distributed over the ocean basin uniformly, but the stresses accumulating on the ocean floor, his point here is that they will not be distributed uniformly, but will be concentrated in certain areas. So this is another important piece of information to understand the process that we're talking about here. And his conclusion is that the uplift, which would be peripheral to the area of unloading, as he says here, to use his words, would involve large and significant displacements. So he finally then says that the physical models show that a variety of deformational effects of significant size can be expected to occur during and following the melting of the Pleistocene ice caps and the resulting eustatic rise of sea level. In Canada, the total amount of rebound at the center of uplift was between 400 and 1,000 meters. So 1,000 meters is 3,280 feet. So think about that. Think about it. A rise of up to over 3,000 feet after the glacial unloading. What would be the corresponding depression on the ocean floor along the mid-Atlantic ridge? Could it be that much?
It'd be a lot. Yeah. Yeah.
Could it be more? Well, that's very possible. Now, if you had a vertical change along the mid-Atlantic ridge of 3,000 or 4,000 feet and a rise of sea level of 400 feet, what's going to happen to any islands that are going to be along?
Yeah, they're going to be submerged very quickly.
They're going to become buttes or whatever they're called. What are they called?
Oh, the
Geoid.
Geos.
No, never mind. Wrong word.
Okay. Interesting stuff, isn't it?
That is, yeah, and it makes sense because the ocean floor is a thin crust. I mean, if it rose up, 3,000 something feet over the continental mass, then you can imagine that thin crust in the ocean, when that water dumps into there, that it could depress a lot farther, especially because there's also a hinge there along the ridge.
Yes. Yeah, that's exactly the point here that I want people to take away from this. Yeah, so then a couple of years later, another scientist, J. Chappell, also in quaternary research, followed up on the research of Walcott that I was just quoting from. And his conclusion was, in 1974, he uses the term hydroisostasy, which is simply talking about isostatic adjustments due to water, right, rather than presumably ice. Hydroisostasy, the concept that meltwater from Pleistocene ice caps produced loadings of ocean floors such that significant global deformation followed, recently has been examined by Walcott. The earlier qualitative assessments of hydroisostasy as an important factor in glacial-eustatism, right? We're just making up a new word here, but it's glaciers and eustacy. So
right.
Glacial-eustatism are qualitatively supported by Walcott, who also demonstrated that the effects of glacial-eustatic inundation, here's the important point, will vary with location. So what that means is if it's not adjusting too much in one place, it has to be adjusting even more somewhere else. To maintain. Yeah, you got it. That's the idea.
Presumably those adjustments it would pick somewhere else that was easy.
Path of least resistance.
Path of least resistance. That's right. Yeah.
Exactly.